All right, so remember we have this data from the calcium and the placebo, and so you would actually need to check your conditions. So if you looked at your own box plot, it's Control-I. You would insert a data and statistics page, and I want to see calcium first. Okay, and then I'm going to change it to a box plot. So I can say, okay, there's no real skewness or outliers. I can change it to a normal probability plot. It's, a little bit of curvature. Okay, so what I'm going to do down here is I'm going to go click on calcium, and I'm going to change it to placebo because I need to check the same things for placebo. I can see it's pretty close to a straight line. And then I can change the placebo one to a box plot as well so I can check it. And I don't have to insert a bunch of different screens. I'm just checking the different values on that variable. So again, there's no real extreme skewness or outliers. So I'm going to go ahead and insert another page, which is going to be a calculator page, because I want to run a test on this data. So I'm going to go Statistics, Stats Test, because I checked my conditions, and now I have a two-sample t-test. And it's going to ask me data or statistics. In this case, I have the data, so I'm going to click OK. List 1 is called calcium, because remember I did the calcium minus the group 2, which is my placebo. I don't need to change my frequency. My alternative is that it's greater than, okay? And notice it asked me if it's pooled. T-tests are not going to be pooled unless our standard deviations are the same, so we're going to assume that they're not the same. So pretty much you're never going to change this. Click OK. And then it's going to output some stuff to us. And here I can see what my t-statistic is, what my p-value is, what my degrees freedom is, my x-bar 1, my x-bar 2, my standard deviation of group 1, my standard deviation of group 2, and so forth. And so I can make my data, now that I have this, look like the way it needs to look. So they did theirs here. If I were to do mine, remember I'm going to do mine a little bit different. So here we go. I'm going to take the values that I have from my calculator. So remember my calculator says that its x bar is 5. So I'm going back. I have 5 minus a negative 0.27, right? 27, right? And then it's going to be minus 0 for the no difference over the standard deviation of the statistic, which is going to take the standard deviation from my problem right here, this 8.74325. So 8.74325, square it over, my first group had 10 in it, plus my standard deviation for my second group was 5.90069. 5.90069 over 11, and that's squared. Okay, so this is going to be my t statistic equals that. So then my t equals, according to my thing, says 1.60372. 1.60372. Okay, so if I draw my curve here, and then I have a degrees freedom, notice it shows me what my degrees freedom is. It tells me degrees freedom is 15.95905. So 15.9505, and when they write that, we're going to know you got that from the technology, okay? And so then it's from 1.60372, and I'm going to shade, and I'm going to tell it that my p-value here would be whatever this is, which says my p-value is 0.06442. So equals 0.06442. And at alpha level of 0.05, you know that you're going to fail to reject. They're showing you that they went with 9 degrees freedom, and it's between 0.05 and 0.1, which is true, it is there, but we're getting the exact value. So as long as you have your t-statistic, your degrees freedom, your curve drawn with your label, and your p-value, you're good. I'm not going to make you write the t-CDF part. All right? So because the p-value is greater than alpha, we fail to reject H naught. Okay, it doesn't give enough evidence that calcium reduces blood pressure. 9 degrees freedom, the critical value for a 90% confidence interval is t equals 1.833. And so here they find the confidence interval, which says that calcium reduces it from negative 0.754 to 11.3. The thing is that it goes from a negative to a positive, so 0 is in here. So the possibility of no difference is a possibility. So our confidence interval here is going to reject the null as well. And they explain that because 0 is in there, right, on a two-sided test, we would reject it as well, just to see if there is a difference, okay? Against a two-sided alternative is alpha equals 0.1 significance level, all right? So because a 0.1 goes with a 90% confidence interval, or against a one-sided alternative of 0.05. Because remember, when I have an alpha level of 0.1 on a two-sided test, that really means that all I have at 90%, right? That means I have 0.05 here and 0.05 here. And this is a 90% confidence level. So a two-tailed test is at alpha equal to 0.1, 10%. But a one-tailed would alpha equal 0.05. And it would still fail to reject it. And that's what they're saying in that picture. All right, using two-sample T procedures wisely. Remember, again, the same thing you had to check for in confidence intervals. Remember, we don't want it mainly symmetrical with no outliers and very little skewness. All right. In planning a two-sample study, choose equal sample sizes if you can. Do not use pooled two-sample T procedures, okay? That's what I told you. Do not use them pooled. We are safe using two-sample T procedures for comparing two means in a randomized experiment. Do not use two-sample T procedures on paired data. Paired data, we're going to have one. So we're going to have to know the difference between a two-sample T procedure and a paired data. And beware of making inferences in absence of randomization. The results may not be generalized to a large population of interest. All right, and then here's your summary of what we went over, and that's all. Yay!